R the positive, and then, so this I can say is V plus 0, this is V minus 0, and then we have R external, and the current goes in that direction. So let's just write down V minus 0. So this would be the standard half cell potential of the negative electrode, which is graphite, you know, and the V plus 0 is standard half cell potential of the positive electrode. The R minus is the interface resistance, the electrical resistance of the negative electrode. And the R plus is the interface resistance of the positive electrode. And R electrolyte is the electrolyte resistance, and the R external is the load or the external resistance. So these are the definitions of these terms. And so let's see. So this is a very simple model, right? So let's examine this model. And first thing we can do is we can simplify that further. So let's simplify that by lumping the circuit elements. So let's lump them as much as we can. So we'll draw like the circuit like so. So we have source V naught, which is V negative naught plus V positive naught, right? So we added the two half cell voltages, and then there is R internal. That's the sum of R negative plus R electrolyte plus R positive, and then we have a external resistance. So this will be the R external, and the voltage across this is that. So in electrical engineering, it's important to draw so once we draw the current direction, by Ohm's law, we have to say this is positive and this is negative. We can't say negative positive because Ohm's law says that V over I is R, is resistance. So if we were to reverse this, then we've got to put a negative sign. So as a rule, this is how we draw resistors and their polarity. Okay, so given that, what can we do? Okay, so V, our external voltage, is I, that's this current, times R external, right? So simply Ohm's law. And now V, this voltage, is also a function of the current and the state of charge. So subsequently we learn how, not today, but later on, how the voltage is affected by the current and the state of charge. But let's assume it for the time being. And just for the fun of it, I can say this is del Q over E. Actually, I should say N, but in the case of lithium-ion battery, N is equal to 1. So E is the electronic charge, or I can say Q. So this is, as we learned before, the Gibbs free energy for the reactions at the anode and the cathode. So just as a note, Gibbs was born and raised in New Haven. So this last Friday, I actually visited the kindergarten where we went to school. So the school still exists. You know? Okay. So let's see. So let me draw the, if I can draw over here, I'll draw the current. Okay, this axis is voltage, and so let me draw voltage on that axis and current on this axis. So when the current, so let's write down the relation between voltage and current. So voltage is equal to, so voltage I said is I times R external. It's also V0 minus I times R internal, right? So V0 minus I internal is also the voltage. So when I is 0, the voltage will be V0. This is the open circuit voltage. So if you break this circuit, we get open circuit voltage. And then if we short circuit this resistance, so the voltage is 0, so I can draw a straight line. So this relationship, V is equal to V naught minus R internal, so voltage here is 0, so this current would be V naught over R internal, right? So if this is 0, the only thing limiting the current is R internal. So V0 over R internal is the open circuit voltage. Open circuit, I'm sorry, short circuit current. So that's what that is. So now what about power? So let's plot power on this axis. So what would that look like versus I? So power is equal to VI. So we know that V is V naught minus I times R internal, and then I multiply by I. So this is power. So let's plot the power curve. So when I is 0, power is 0. So one point is over here, and so let's see what else. What would happen at this point? So at this point, we can say right here, the power is equal to V0 minus I. I is V0 over R internal times R internal times I. So power is 0, right? So we get 2 points over here. And if we draw the curve, it look like this. So the power has that shape. So the question comes up, what is this maximum power and what is the current at which the maximum power happens? So for that, we can do our simple introductory math. So we differentiate power by di. What do we get? We get V0 minus, okay, so let me write this. So it's V0I minus R internal I square. So first, when I differentiate this, I get V0. When I differentiate second term, I get 2R internal times I. And we know when power is maximum, this is 0. So therefore, the I at which power is maximum is equal to V0 over 2 R internal. So therefore, P max is equal to, so we insert over here, we get V0 minus, so I is V0 over 2 R internal times R internal times I, which is V0 over 2R internal. So if you were to simplify this, you get V0 square over 4R internal. So this would be V0 square over 4R internal, and this value of current we already calculated is V0 over 2R internal. So this is a simple DC analysis, just an introductory kind of presentation. But we want to know what's happening. If you want to know what's happening inside the battery, then you need to do AC analysis. And so people have done that, and one of the simplest ways of representing this cell electrically is a circuit that looks like this. So this is RS, this is RP, and this is capacitance C. So this would be the simplest way of representing what's happening inside this battery. This RP is called polarization resistance, and RS, let's see, RS is, of course, that's series resistance. That's probably has to do with the, so this would be the resistance of the electrolyte. So solution, so electrolyte is solution resistance, and the C is the capacitance of the electrodes, the electrode surfaces. So this is the simplest RC circuit that we can use to represent the cell. It gets more complicated than that, but today let's try to understand this circuit by actually not using any math. So we'll use mostly a graphical approach, which I called the symptotic approach. So what we'll do is we'll draw the Bode plot of the circuit, of the impedance. So we're interested in the impedance of this. So from here to here, we're interested in the impedance. So this would be the AC impedance, right? Impedance is AC. Okay. So first step is, so we'll go in two steps. First step is we'll plot the Bode plot of this impedance, and second is we'll do the Nyquist plot. So that's what we'll do today. Okay. So essentially what we have, one way to look at this is to say that here's a cell and we apply certain voltage to it, and as a result we get a certain current, right? So from this we can get impedance. So impedance would be like V over I. So this is the time domain. So this is time domain. But we like to work in the frequency domain. So I'll give an example, a very crude example of why we like to work in frequency domain. So look at this circuit. If we apply a voltage, let's say voltage as a function of time, so this is like sinusoidal voltage, and it has a certain frequency. So we're applying voltage across, say, a certain frequency, and we're measuring the current, and that's how we can get the some idea what's going on. That's how we can get the impedance, right? So suppose the frequency is 0 of this voltage, then our impedance will be Rp plus Rs, right? Because when the frequency is 0, this is infinite impedance. So when the frequency is 0, we get Rp plus Rs. So we get some idea what they are. Now, when frequency is infinite, what happens? The capacitor is short-circuited. Then our impedance is Rs. So so this way, by looking at two different frequencies, we know Rp and Rs, Rp plus Rs, and by looking at infinite impedance in frequency, we get Rs. So from this information, we can get Rp and Rs. But we still don't know what is C, so therefore, we have to go through, instead of just two frequencies, we like to do impedance in many frequencies. So that's frequency domain analysis. So this way, we can understand what this circuit consists of. So as a first step, let's plot the Bode plot of this circuit. I think I can go to the middle. So what we're interested in is, again, we have our cell, a battery cell. We are applying a voltage, but now as a function, voltage at many different frequencies, and we're measuring current at the same frequency. So I've drawn S. Now what is this S thing? So S is complex frequency. And don't worry too much about it today. S is sigma plus j omega. So this is like a damping factor, and omega is the angular frequency. That's 2 pi f. F is in hertz, right? Cycles per second. And so that's what omega is. So today, don't worry about damping factor. We'll just say, we'll just only take care of, we'll only have omega in our frequency. So this is like just frequency, right? Okay. So in this system, you can think, so this voltage, if I write this in time domain, it could be V, which is a constant, sine omega t, and the current would be some constant sine omega t plus theta. So if I have a voltage input, I'll get a current output, and so the ratio of the two, let's say V over I will be the magnitude of this impedance, and this theta is the phase shift. So we're interested in the magnitude and the phase. So what we want to do in Bode plots is to plot the magnitude versus so I'm calling m the magnitude versus log of omega, and we plot the phase difference between the voltage and the current versus log of omega. So that's what Bode plot is. The magnitude of the impedance and the phase of the impedance. So we will plot this now for this circuit, for the circuit over here. So I'll just clean up this area. So I'll draw it over here. So before I tackle this somewhat complicated circuit, let me do the Bode plot of a pole, a single pole. So I'll describe you what a pole is. So if I take a simple circuit like this, I have V1 of S, and I have a resistor R, and I have a capacitor C, and the voltage across here is V2 of S plus minus. So I'm just using this as an example. So the transfer function, which is like impedance, so impedance is a transfer function between voltage and current. Here I've taken another example. The transfer function is between V2 and V1. So we have defined a new term called transfer function. So this I call it G of S is equal to V2 of S over V1 of S. So we want to plot the Bode plot of this for this circuit. The reason I picked this circuit is this is what we call a pole response. So let me explain what that is. So V2 of S over V1 of S, if you do the math, see V2 is proportional to this impedance, the impedance across a capacitor. That is 1 over SC. So impedance here is 1 over SC. And V1 is proportional to the complete impedance. So it's R plus 1 over SC. So this is our transfer function G of S. So let's simplify this. We multiply top and bottom by SC. We get 1 plus RCS. And then what I do is I normalize this. So I put it in a different form. I take out this RC outside. So I have, okay, so what I do is I say 1 plus S over 1 over RC. So I'm converting this form here, and I say this is equal to 1 over 1 plus S over omega naught, where omega naught is equal to 1 over RC. So the reason I did this is this is my standardized form. So this is what I call normalized form. So anytime I want to do the Bode plot, I put the function in this form. Okay, so the Bode plot of this. So we use a technique called the asymptotic approach. So I think I'm going too fast. So if there are any questions, let me know, or I can proceed. So basically what I'm doing is I'm trying to solve this circuit, but before I do that, I'm going in baby steps, and I'm first looking at, see, this circuit has two things. It has a pole and a zero. So I need to explain that. So I'm first explaining what a pole is, then I'll explain what a zero is and how to make the Bode plots of these poles and zeros. So this is a function. So now we have a function, G of S is 1 over 1 plus S over omega naught. So we need to get the Bode plot of this. And to do that, what I do is I replace the S with 1 plus J omega over omega naught. Remember I said earlier that S is a complex frequency is sigma plus j omega. I'm not including sigma, I'm just including j omega. Now this, so I can say that g of j omega is equal to 1 over 1 plus j omega over omega naught, right? And then I can say the magnitude of g of j omega is equal to 1 over 1 plus omega over omega naught squared. So everybody knows this, right? So the way I got this is I multiply the top by minus j omega over omega naught, and I multiplied the bottom by the same term. So I should have, instead of going there directly, I should have gone there. So I get the magnitude to be this, right? And so I could, so let me just rub this off and write down what this term is. So this term is 1 plus omega over omega naught squared. So we have these two terms, actually the same thing. So this is the transfer function, and this is its magnitude. So we know the so let's plot the magnitude Bode plot. So notice over here that, so this g of j omega is equal to 1, or let me put another way. So when omega approaches 0, when omega is almost 0, g of j omega will be, so when this omega is 0, this term is 0, so we have 1 over 1, so g of j omega is 1. When omega goes to infinity, then g of j omega is equal to what? So let me walk slowly over here. When omega is infinity, this term becomes infinity. 1 over infinity is 0, right? Okay. Let's see. Okay, so I made a mistake over here. When this term is very high, we can neglect the 1, right? So when omega is high, this term becomes high, so we neglect the 1. So this term becomes omega naught over omega. So it's not 0, it's omega naught over omega. So I should just say, instead of say infinity, I should say high. When omega is large, the transfer function becomes omega or omega naught. So now we need to plot this on the Bode plot. So on the Bode plot, we don't plot just the magnitude, we plot its dB value. So what is dB value? So g of j omega dB value is 20 log of g of j omega. So essentially, we take the g and we take the 20 log of g, that gives us a dB value. So 20 log of 1 is 0, right? So in the low frequency range, the magnitude is 0. In the high frequency range, so in this high frequency range, we get 20 log of omega or omega naught. So now that means that this term So let's see, did I make a mistake over here? Oh yeah. So I should have put omega naught over omega, right? And this is minus 20 log of omega over omega naught. So notice that in the low frequency range, the dB value is 0 because of this 1. So 20 log of 1 is 0. In the high frequency range, the slope is minus 20. So this is minus 20 dBs per decade. And this is omega naught. So when omega is equal to omega naught, this term is 1. And 1 times minus 20 is 0. So this is the Bode magnitude plot for the Bode. Now what about the angle? So now we're concerned with the phase angle between V2 and V1. And for that, look at this equation over here. This is the transfer function, and it has 1 minus j omega or omega naught. So the angle term is hidden over here. So let me use this space over here. So now we're interested in the phase of the plot, and the phase is given by the information is in this numerator. Denominator has no phase. See, denominator has no j term. So this we can draw on the S plane. We can say this is the real and this is imaginary, and we can say the real term is 1, the imaginary term is minus j omega or omega naught. So this is the magnitude and that's the phase. So this magnitude is same as this one over here. And the phase, notice that when omega is 0, this point comes here. So you basically have this vector is horizontal, 0 angle. So there is, in the low frequency range, your phase is 0. So as omega increases, this point moves down, so the angle goes to minus 90. So the angle moves to minus 90 degrees. So this is the Bode plot of a pole. And the pole has the transfer function 1 over 1 plus s over omega naught. So that's what the pole is. So pole has the magnitude at 0 that bends down to minus 20, and the phase goes from 0 to minus 90. So I've taken the asymptotic approach. So I only told you what's over here, what's over there, what's over here, what's over there, and there's a transition over here. That's really not important right now. So this is the pole. And the next thing I want to do is to talk about a zero. So poles and zeros are the things we're concerned with. Once we understand poles and zeros, then we're doing fine. So I know I'm going really fast, but I'm trying to be as slow as I can be. So let's look at 0. So what is the Bode plot of a 0? So first let's take an example of a 0. Now this example of 0 I'm taking doesn't exist in electrochemistry, but it's convenient. So let's take a circuit like this, and we're interested in this impedance. So this is our resistor, and this is an inductor. I don't think we'll come across inductors in batteries, but this is just to explain what a 0 is. So this impedance, Z of S, is equal to what? R plus this impedance, right? R plus SL. So the impedance is that simple. And now I need to put this in a standardized form. So I take R outside, I get 1 plus S L over R, right? And then to put it in a normalized, standard normalized form, I say S R over L. So in this, I can again say this R1 plus S over omega Z. So the R over L is omega Z. So this is my standard normalized form. So once I get to this form, once I solve this circuit, then in the future, when I see this expression like this, I can just make the Bode plot. So let's make the Bode plot for this. So we have S, we replace that by j omega, so we get R. So let's figure out about R. R is just a constant, right? So let me get rid of that. So I get 1 plus j omega over omega z. So in reality, you need to include the R, but the R is just a constant, so we can ignore it. So then I can say that the magnitude of this term is 1 plus omega over omega z squared square root, right? So when omega is small, the magnitude of z is equal to 1, right? When omega is, let's say, 0, we can ignore this term. Square root of 1 is 1. When omega is high, then the magnitude of z is omega or omega z, right? Because if this term is large, then 1 disappears. Okay, so the Bode plot for the magnitude plot will be like this. So here we are plotting the dB value of these magnitudes. So when z is equal to 1 in the low frequency range, this is 20 log of 1. It's basically 0, right, in this range. In the high frequency range, this equation will be 20 log omega over omega z, 20 log of this. And they meet at omega z. And this slope is 20 dBs per decade. So this is the Bode plot, the magnitude plot for the 0. What about the, oh, this is log of omega. What about the phase? So the phase information is over here. So just like last time, let's draw on the S plane, we have the real axis and imaginary axis, right? So we have 1 on the real axis, then we have j omega over omega z, j omega over omega z on the imaginary axis. So this is the magnitude and this is the phase. So notice when omega is equal to 0, this term comes down here. So the phase is 0. And then when we increase omega, this point goes up and the phase goes to 90. So the phase goes to 90 degrees. So this is the phase of the Bode plot, and that's the magnitude. So now we're done the Bode plot for 0 and for the pole. Now let's go to a problem at hand, which is this circuit. So let's just get rid of everything over here. So now we'll solve that circuit, and we'll get the Bode plot of this circuit. Okay. So let me draw the Bode plot. So this is the simple graphical approach. Log of omega over magnitude of this in dB. So when you look at the circuit, the R sub S, what is this dB? What is it in terms of dB? It's 20 log of R sub S, right? So let me draw R sub S is dB value. So I took RS, took its log, multiplied by 20. So this is the Bode plot for that resistor. It doesn't change with frequency, right? Now RP, let's draw the Bode plot of RP in terms of dB. And that's simply the magnitude of RP in dB will be same 20 log of RP, right? Again, a straight line. So these are Bode plots for the two resistors. So what about the Bode plot for the capacitor? So capacitor, we know its impedance is 1 over SC, right? And I can say is 1 over j omega c. So it's inversely proportional to omega. And if I were to have Z sub c in terms of dB, it is 20 log of 1 over omega c, which is minus 20 log of omega c, right? So right away we know it's a negative slope of minus 20 dBs a decade, right? So that's the capacitor 1 over omega c term. So now what we do is we say if you have two elements in parallel, the smaller one dominates, right? So RP is this, and RC and C is that. So smaller one dominates. So the impedance of the parallel circuit will be like this, right? The smaller value dominates. And then when you take this circuit and that circuit, they are the series, so the larger one dominates. So this becomes the Bode magnitude plot for this circuit. See how quickly we did it? We didn't do any math. And we know what these corner frequencies are. You can calculate them. So that's the Bode plot magnitude. What about the phase? The phase is also straightforward. So let's plot the phase. Okay. So this, this is a pole. See? The same as this. So this, by inspection, we know this is a pole, and by inspection, we know that's a 0. And we know the phase of a pole. So for a pole, we start at 0, and then we go down to minus 90. And this is 0. And for 0, we know we start at 0. So this would be the phase for 0. So now, in Bode plots, you add things. So I didn't mention that before, but in Bode plot, you add terms. So we have two phases, one from the 0, one from the pole. When we add them, just simple arithmetic addition, you get a plot that looks like this. So this is the phase of this circuit. So here's the magnitude, here's the phase. So we have solved we obtained the Bode plot of this circuit. And this is the simplest common circuit for batteries. Now, for some reason, which hopefully I'll explain next time, is people, this is okay, but people like to plot in terms of Nyquist plot. So what Nyquist did, I don't know where he was born, like Gibbs, but what Nyquist did is he combined these two plots into one. And people in control theory love Nyquist plots. So here we have magnitude as a function of log omega. We have phase as a function of log omega. But we want to shrink these two into one plot, and that's the Nyquist plot. So what's a simple qualitative way of getting the Nyquist plot? So in Nyquist plot, we have the real axis and the imaginary axis. And so what we do is we say, we examine the Bode plot. So this is low frequency, like zero frequency, low frequency. We have this much magnitude, so let's say this is 0. So this much magnitude, and it's kind of constant, and our phase is 0. So to start off with, we have a large magnitude, and the phase is 0. So let's draw this vector. So we start at 0, we have a large magnitude, and its phase is 0. So this is what it looks like. And this point is this. Now this we said is RP, right? But actually at 0 frequency we know it's RP plus RS. So we had to ignore RS. So actually this point is RP plus RS. Because we're dealing, so this is for omega equals 0. So we are starting at very low frequency. So we have RP plus RS. Now let's increase the frequency. Let's go to, let's say, somewhere over here where the magnitude is about the same, but the phase is getting negative. So we have negative phase. So this is negative, slightly negative. And the magnitude decreased on a little bit. So let's go to this frequency. So now the phase is decreasing and the magnitude is decreasing. So phase is going negative and the magnitude is decreasing like this, like this. But then what happens is, let's suppose at this point, a phase is 0 and a magnitude is small. So we end up with the small magnitude and the phase angle is 0. So we get a curve like this. So like I said earlier, we started RP plus RS. Now where do we end up? We end up here at high frequency. The magnitude is RS. So this is RS, this is RP plus RS, and this is a semicircle which I did not prove. I did not prove that this is a semicircle. So this is the Nyquist plot for our electrochemical circuit. So hopefully in future lectures we'll use Bode plots and Nyquist plots. So I think that's all for today. Any questions? I covered a huge amount today. I skipped a lot of steps, but some of you already have done this before, right? So for example, I missed the step. Why do we add the Bode plots? In other words, we had 2 Bode plots. Well, actually we had 3. We had Bode plot for 2 resistors and a capacitor. Why do we add them up? And that's, I ignored that step. And then I also said the phase plots also we can just do a simple arithmetic addition. And the reason we can add them up is because when you multiply and when you take a log of multiplication, you're actually adding. So that's the reason why. Because we are on a log scale, when we multiply terms, the log terms are added. That's the reason why. Okay, on that note, I'll call it a day. Oh, let me see, any questions over here? Oops.